So good morning and welcome to our fourth year project presentation. Our project's topic is IoT for campus, enhanced campus security and safety. This is our hardworking team. My name is Omar, and I'm in computer systems engineering, and I work on the analytics part of the project.
I'm Kenan. I worked on the networking part of the project mostly.
I'm Reda. I worked on the camera element of the project.
I'm Mohammed Al-Digs. I'm an electrical engineer. I worked on the integrated sensors.
I'm Majeed Mirza, and I'm a computer systems engineer as well, and I worked on the back end of the project.
My name is Hooseon Yim, and I'm working on the mobile app for this project.
Awesome. So just a brief outline of what we're going to cover today. So we'll start with our technical objectives and goals of what we started the project with, and then we'll go over the system architecture and then the different components of the project. So we'll explain what we did for each component, and then at the end we have a demo video. So we tested out the whole system in the tunnels in the bottom. So we have a video for that. We'll watch that at the end. So the goals of the project are mainly, so Moore's law says technology is rising up exponentially, but we can see that the campus technology is, like the safety technology more to say, is not, catching up. So our project aims to get that emerging technology of the 21st century and integrate that with the campus security. So the main goal was to have an IoT system where you have different nodes and they're all connected to each other, and they exchange data, and then we can do analytics and have smart decisions taken all the time instead of just independent nodes in the tunnels. Another thing was that our project doesn't aim to make a product out of the system. It's more to do a feasibility study of how this can be applied to different campuses across Canada.
Okay, so our technical objectives, as Omar stated, is to deploy multiple sensors around campus. So these sensors can include temperature, humidity, flooding sensors, which are basically water sensors, air quality, sound sensors, in addition to cameras. We are also aiming to create a mesh network for the IoT system, and we will be using Wi-Fi and Zigbee for that, which is the 802.15.4 protocol. So we also aim to effectively gather data through the mesh network and to do data analysis on that data from IBM, Bluemix. We will also have two apps, one for security personnel and one for campus staff and faculty and students, so they can monitor temperatures, or they can be warned of any alarms or any emergencies that could be happening around campus. And again, this project is just for testing and feasibility. It's not meant to be deployed in any way or to replace the current system. So this is basically the architecture for our system. We have two types of nodes. We have the Zigbee nodes and the Wi-Fi nodes. The Wi-Fi nodes connect directly to a router, and then the Wi-Fi nodes send data from that router to the server. Then we have the database on that server, the app connects to the server, and Bluemix connects to that server as well. So now Reda will cover the camera for the project.
So hello everyone. So today I'm going to be talking about the first element in the project, which is the camera. So I want to start my presentation with introducing the Raspberry Pi camera and with a brief definition. So what's the Pi camera, Raspberry Pi camera? So it's a high definition video camera with 8 megapixel sensor, and it connects to the Raspberry Pi board via a small cable. And if you're wondering why did we choose this camera to deploy it in the system, it's because it can be integrated with sensors, and also it can record videos in case of an emergency. So that's the Raspberry Pi camera. So this is a demo circuit we created. We integrated with a temperature sensor, as you can see on the right side. The temperature sensor, it's on the breadboard, and that's a buzzer for the alarm. And this is the Raspberry Pi camera with the connected to the Raspberry Pi board. And in the next slide, I will explain how does this circuit works. So I created this real-life scenario to show you how the circuit function. So let's say there's a fire event. The sensor, the temperature sensor, will detect the fire, and as soon as the sensor detects the fire, it's gonna activate the alarm and at the same time start recording. So the recording happens 30 seconds before the fire event, and it keeps on recording a post video, a 30-second post video. And the nice thing about it also, it keeps on recording videos as long as the sensor is detecting an abnormal event, and then all the recording videos are sent to the Google Drive. So the Google Drive view, we have a folder called emergencies in the Google Drive. So these are previous videos recorded from previous demos we had. And the other camera I'm going to be talking about is the Foscam IP camera. It's a wireless IP camera with a built-in microphone and motion sensor to detect movement or noise. And the main use for this camera in our project is for live streaming and using the Foscam app. It's an external app, and also to record emergency videos and save it on the Google Drive too as well. Mohammed Al-Digs will be talking about the sensors.
Hello again. I'm going to be talking about the sensors we used in our project. So here we have the MQ2 smoke sensor and the MQ7CO sensor. They're both analog and they give an output voltage of 5 volts, but we had to drop that to 3.3 volts using a voltage divider because the Raspberry board doesn't support anything higher than 3.3 volts. And we added an ADC converter to convert the analog values to digital values based on the algorithm in the datasheet to convert from voltage values to ppm, which is particle per million. Here we have our DHT22 temperature and humidity sensor. It's digital. It also, what's the good thing about it, it measures temperature ranging from -40 to 80 with an uncertainty of 2 degrees, as well as the humidity in air ranging from 0 to 100% with the same uncertainty, 2 degrees. It also has a sampling rate of 0.5 hertz, which gives us a reading every 2 seconds. That keeps the system updated. The minimum voltage for the sensor to operate ranges from 3 to 5 volts, and it's connected through a GPIO pin on the Raspberry Pi. Here we have our air quality sensor. It's a digital sensor that's connected through an I2C bus. It measures carbon dioxide, temperature, and TVOC, which is the total volatile organic compounds, such as natural gas, alcohols, and organic acids. Here we have our microphone. It's a digital sensor that's connected through an I2S bus. We got the sensor to record audio in a waveform, so we can, if there's an emergency, it also records some audio file. Here we have our water sensor that our great colleague Kenan designed from scratch. So when the probes are submerged in water, it creates a short circuit over here, which gives us lower resistance than what we have here, making the current flow to the GPIO, which gives a high signal of a 1. Otherwise, it's gonna go to ground and give a signal of a 0. This is the node architecture. It's not all the nodes are the same, but this is one of the samples. So we have the emergency button connected to the Raspberry Pi using GPIO. Also, some smoke sensors, sound sensors connected to I2S, air quality on I2C. This is the general architecture for a node. And here we have the 3D printed model for the, as you guys can see, this is not like a suitable presentable thing to be placed in a place. So I designed the 3D model. It's basically a box that opens from one side, and it has a bunch of holes in it, so the smoke and gas sensor can detect if there's any abnormal event. And we added the university logo, our lab, sensor systems, and Internet of Things lab. And we also added the website. And now I'm going to hand it back to Kenan.
Okay, so now I'm going to cover the networking aspect of the project. As I said in the beginning, we have two protocols that we're using. We're using Wi-Fi, which is already built in the Raspberry Pi, which is one of the main reasons why we chose the Raspberry Pi 3B, and the Zigbee chips, which is the 802.15.4 protocol, which are these guys over there. They're made by a company called Digi. And yeah. So basically, every node can be a Wi-Fi node or a Zigbee node, depending whether it has Wi-Fi signal or not. So a Wi-Fi node has multiple responsibilities. One of these responsibilities is obviously to read its own sensors and save that data into a local database. It also requests addresses from the Zigbee nodes in order to discover what nodes are around. It requests data from those Zigbee nodes, sends data to the server through Wi-Fi. And how that works is, basically it's a sync function, so it's not just sending data to the server, it basically tells the server that I have data for this node, for example, node 1, node 2, node 3. Server sends dates for those nodes when they were last updated, and then the Wi-Fi node will send data after that date. So that way we have two databases storing the data, one on the server and one on the node itself. The other thing is, the Wi-Fi node will always listen for alarms that are coming from the Zigbee nodes. So the Zigbee node always listens for requests from the Wi-Fi node. It reads its own sensors, stores data in the database. Whenever it gets a request from the Wi-Fi node, it will either send its address if it's a discovery request, or it will send the data for the readings of the sensors. It will also listen for alarms, broadcast alarms as soon as they happen. A Wi-Fi node picks up the alarm and sends it to the server. And the other responsibility for a Zigbee node is to bridge other Zigbee nodes so data can hop through all the way to a Wi-Fi node. So this is basically our mesh architecture. So over here we have a router, and all these guys are Wi-Fi nodes around the router. And here are our Zigbee nodes. Zigbee nodes, we have implemented the multi-hopping function. So basically, this node won't be in range of this guy. And what happens is data will go through these all the way to the Wi-Fi node, which will then go to the router and send it to the server. What happens is our Wi-Fi nodes also can be Zigbee nodes. So in case this router goes down, all these nodes will turn into Zigbee nodes, and then one of the Wi-Fi nodes here will pick up all the data for these guys and send it to the server. So the range between the Zigbee nodes we have is about 30 meters, and that's limited by the chips we're using. It can also be extended if we buy more expensive chips that have bigger antennas. Those chips can have ranges up to like 1 kilometer or something like that. So again, basically putting that in writing, we have a Wi-Fi node that sends a discovery packet. Zigbee nodes reply with their addresses. The Wi-Fi node then goes and asks each individual Zigbee node for its data. It receives that data, stores it in its local database, and sends it to the server. And it loops again and does that. at any given time, if a Wi-Fi node senses that a threshold has been crossed for any of its sensors, it automatically posts that to the server, which will then be used to send a notification on the app. If a Zigbee node detects an alarm, it broadcasts it right away, and the Wi-Fi node picks it up and sends an emergency immediately to the server. And these are basically the main scripts that we're using to implement that. We have the main script that is basically a Python script. It's automatically launched on the Raspberry Pi as soon as we boot it up. It handles networking for both Wi-Fi and Zigbee. It handles the data storage with, say, locally. It also handles sending the data to the Wi-Fi nodes, to the server, sorry, I mean. It validates the data and checks the thresholds for emergencies and requests sensor readings from the sensor helper. The sensor helper is basically just a script that integrates all the sensors together in one place and handles all the low-level code for reading out the sensors. It also handles the calibration of the sensors when the Pi first boots up, because we have our smoke and CO sensors that need calibration. And it also handles a separate thread for the audio, for the microphone, so it can keep constantly recording. We also have a bash audio script. That script basically records 2 seconds of audio every 2 seconds and then analyzes that audio using a tool called SOX, which basically analyzes the amplitude of the audio file. And if that amplitude goes above a certain range, then we have a noise alarm or a noise warning. Finally, we have the mesh functions object, which basically handles the creation for all the packets that we have for either Zigbee or Wi-Fi. So for Zigbee, we're creating our own packets with the data format in them and headers to indicate whether it's a discovery packet or it's a data packet or it's an emergency packet. Next up, we have our deployment diagram. So we chose to basically implement the system in the tunnels and show how it would be deployed in the Carlton tunnels. And we actually walked through the tunnels and we mapped it out depending on the Zigbee ranges and the Wi-Fi ranges and where we have Wi-Fi access and where we don't. So in the end, we ended up with 44 nodes that are Wi-Fi, 17 that are Zigbee, and 17 routers and 20 IP cameras. And that would cover the whole tunnel system. And again, on this diagram, you can see the Wi-Fi nodes are blue. So over here we have Wi-Fi access, but once we get there, we don't have any Wi-Fi, so it has to be a Zigbee node. And over here in the long stretch, you can see there's no Wi-Fi whatsoever. So all these guys would be Zigbee nodes. And then, of course, if any of the routers go down, they will automatically switch to Zigbee, and that way the system will stay up. So for our demo, which we have a video of and you'll be seeing later, we chose this section of the tunnel, which is basically, if you know, the exit from the architecture building to the main tunnels, and then going towards there. All these are Zigbee nodes, so that way we can show you the multi-hopping function of the network, and we have 2 Wi-Fi nodes. And now Majeed will cover the back end of the project, which is the server and the database.
So I'll be talking about the back end of the project, the server and the database, as Kenan mentioned. The back end of the project consists of a Node.js server, a MySQL database, which are both, and MySQL database, which are both deployed and hosted using Amazon Web Services. And the server is also integrated with external components such as a Nest smoke detector, and it connects to internal components that are owned by the project through an application programming interface, which we are using a RESTful API. So next, I'll just give an overview of the data flow in our project. So from the mesh network, basically the server is the center of our project where all data flows through, and any component that wants to access this data has to request it from the server. So for example, if the app would like to request request for logs, The logs would come from the mesh network, which would be received at the server. The server would store these logs on the database, and then once the app requests for these logs, the app would request it from the server from the RESTful API, and the server would query the database using SQL and retrieve those logs, and then return them finally to the mobile application. So this is for all the components. So for example, IBM Bluemix works the same way, in which it requests data logs from the server pulls them from the SQL database using SQL queries, and then returns the data requested, and this is also all through the RESTful API. The one exception, or the one special case, would be alarms. So because emergencies take priority over all other data in our project, so if an alarm comes from the mesh network, it is immediately sent to the server, as Kenan mentioned earlier. So the server will immediately get the alarm, and instead of storing it in the database, it'll right away push a notification to all mobile devices that are pointing at the server. So I'll go into more detail about the Node.js server. So the server is written in JavaScript using Node.js, which is a JavaScript runtime environment for running server-side code in JavaScript. We use express.js for the framework. We use the express.js framework for the RESTful API in a project with Node.js. So basically, this what Express does is makes it easier to implement the REST API. The server handles all logs coming in from the mesh network, and also handles all outgoing logs by retrieving it from the database and then sending it to the front end parts of the project. The server handles sending out emergency notifications immediately once received from the mesh network, and it also validates incoming data. So any logs coming in are validated by the server to ensure that they are coming from the correct places. So, for example, if someone were to create a new node that was not registered with the server would ignore that data until it's registered with it. So all incoming data from that new node would be ignored until it's registered. The server also handles the database logic to return requested data, so all queries are stored on the server. So if a request comes from the mobile app, the server will run a certain query to retrieve that requested data. And the server also has the logic to sync with the mesh network, as Kenan stated earlier. So the logic would be that the mesh network sends a request, the server returns what it needs, and then the mesh network will return back what the logs requested. So this is an example of the console logs of the server. The first two are test emergencies, and they are ignored. That's why they say ignored, because they're tests, and we do not want them to be forwarded to the mobile application. So the first one would be a flooding and high carbon monoxide count at this time on this node. And then the second one would also be a test one. The last one is an actual emergency we sent that was pushed. So the response is that 5 recipients received the alarm notification on their mobile phones. Because we have five clients registered with the server, and then the alarm was a fire event on node 1 at this time. So next I'll be speaking about deployment to the cloud. So the server and database are hosted with AWS Amazon Web Services, and the benefits of using Amazon Web Services versus other deployment programs is that there's virtually no downtime when deploying our server. So basically, when I'm updating the server will I'll push the new code to AWS. AWS will boot up that new instance, but will not stop the running instance until the new instance is ready. And then once the new instance is ready, the old instance will power off, and it'll start using the new instance. The MySQL database is backed up automatically, so any production data if some corrupt data comes in or some error happens and we lose data, we have backups of it, and we basically will never lose production data. It's also secure and scalable. So from AWS provides tools for blocking IP addresses, and so technically we could only allow certain IP addresses, for example, the IP addresses of the nodes or so certain router, to access our API. And it's scalable because Amazon can automatically boot up instances of our server whenever there's traffic. So that way, if there's ever too much traffic, Amazon would Amazon Web Services would boot up new instances which would be able to handle them. And technically, the one instance should be able to handle hundreds of requests simultaneously, so it shouldn't be a big deal if there's a lot of traffic. So next I'll be speaking about the MySQL database structure. So in our database we have two tables. We have the nodes table and the logs table. In the nodes table we store all the data on specific nodes. So for example, we store the node ID, the node name, the node location, so the latitude and longitude in the tunnels. We store the node type, whether it's Wi-Fi or a Zigbee node, the last time it was synced with the server. So this is the last time the sync algorithm was run between the mesh network and the server for that node specifically, and the last emergency. So so this is the last time an emergency occurred, and this means that no emergency occurred on that node yet. So for the next table, the logs table, we store all our logs. We store the node ID, the time of the log, the status of the node at that time. So the status saying CO2 means there's a CO2 emergency or there's a high CO2 count in the air. TVOC would mean it notices high amounts of TVOC. And then normal means that it detects no emergencies at the moment. And then all the sensor values are shown here. So when they are 0, that means nothing is detected or that node doesn't have that sensor on it, because all nodes don't have all the sensors. So next I'll be speaking about the integration with the components of our project. So as I said earlier, components integrate with the server using the RESTful API, which allows external components to modify and access data in the database. We use this JSON object as a data model for our logs, which is used basically throughout our whole project to communicate between components. So this log or this JSON log could exactly flattens out to one row in our logs table. So for example, I have the node ID, temperature, status, time, and all the sensor values. If I were to go back, you would see node ID, time, status, water, and so on. So that JSON object maps out to one row. The server is integrated with the database. It just does SQL queries to retrieve data. The server is also integrated with the mesh network via the API, as well as the mobile app and Bluemix, also through the RESTful API. So the server also integrates with external components, such as the Nest smoke detector through an API provided by Nest. So this is the Nest smoke detector, and Google, which is Nest is owned by Google, and basically Nest provides an API to access all the statuses, basically the status and the whether it detects smoke or not, or whether everything's okay, and whether it's online or not, or connected to Wi-Fi. And then lastly, the node camera videos are accessible via Google's API for the Google Drive. And now I'll pass it on to Hooseon, who will talk about the front-end project.
Hello again, and I'll be talking about the mobile app for this project. And before I talk about the functionality of the app, I would like to briefly talk about the technology I'm using. I'm using Ionic framework, which is one of the most popular hybrid mobile app development framework. And hybrid apps are built with web technologies such as HTML, CSS, and JavaScript. And one of the biggest benefits of hybrid apps is that they are built with same code base and they can be launched in multiple platforms, including iOS, Android, Windows, and BlackBerry. And although it is built with web technologies, it can have direct access to native APIs, so it can access mobile devices, internal storage, or camera, etc. So the app serves mainly two purposes. It provides the sensor data collected from the nodes, and it also pushes notification in case of an emergency. And here's our app icon, and if you just tap on it, it'll launch the app. And this is our main page of the app. So the app consists of multiple pages serving different purposes. Right here in this page, I'll be talking about the list page. The list page shows a list of the nodes that are deployed. As you can see here, if you press on it, and you press on the list menu, here are all the nodes we have deployed. And you can press on the individual node to get their information. You can also scroll down to refresh the page. And like Majeed mentioned, I'm using RESTful API to make a request to the server to retrieve all the data. Next, we have a logs page. So this page provides a history of all nodes data. So I go to the logs menu, and here you can see that all the logs are separated by the timestamp. You can also scroll down bottom to get older logs. And you can see that there's a show all button in here. It is a filter, and if you press on it, you'll see all the nodes value, nodes ID. Like here, I press node 2, and it'll only show the values of node 2. Likewise, if I press node 3, it'll show the values of node 3 exclusively. Here we have a nest page. It is a simple page that shows the status of the nest. And like Majeed mentioned, it shows the status of the nest, like if it's online, when it's the last connection, status of battery, CO, and so on. Next, we have an interactive map. So the map is built with Google Maps API, and it shows the location of the nodes we have deployed. So in here, press the map, and here are the arbitrary location for our nodes. You can also zoom in and zoom out. Also, you can press on the individual marker to get the node information. Like this, tap on the information. Then it shows the sensor values, just like what I showed before. Likewise, I can scroll down to refresh the page. Notification system. So it receives a notification if the server receives a emergency status from the node. So if you see here, you see the bell icon over there, and if I scroll down, you can see that I received a notification from Campus Safety app saying emergency flooding and high CO count detected at IoT lab. And if I press on the notification, it'll launch the app. And it'll also take you to the map page. And here you can see the node that detected the emergency is indicated with the animation. You can also press it to get the information. So yeah, that is it for the app. And I'm going to pass it to Omar, who will be talking about the data analytics.
Thank you. So for data analytics, we're using IBM Bluemix, which is IBM's IoT platform that allows us to analyze, view, and manage the data we receive from all the sensor nodes. So this is the first technology we'll be talking about. It's pretty much where we can create flows. So this is where we fetch data from the database that Majeed was speaking of earlier. So we use RESTful API, get the data from the server, and then use JSON to format the data. So like Majeed was showing the JSON data model, that's how we filter it out and then send it to IBM Bluemix. And then here we can see the dashboard. So this is now IBM Bluemix, how it looks. This is where, for example, in our scenario, it would be the campus safety department that would have access to this. And these are called cards, and you can make multiple cards. So for example, this card has humidity. So it's going to show all the values of humidity for all the different nodes that are sending data. Same thing with the timestamp. The water level is 0 right now, which is good. There's no floods. For example, in these cards, you can see the TWOC, CO, CO2, smoke, and the temperature. So you can see the different temperatures. One really cool thing we found, because we already have temperatures, although this is out of the scope of the project, one good thing you could do is that you can even regulate the heating in the tunnel. So if it's already heated up, you don't really have to run the heater, so you can save energy as well. But that's how we can see. And the other cool fact is that we can even deploy this for different parts of the campus. So one dashboard for Mackenzie, one dashboard for River Building, one dashboard for University Center, etc. There's also different kinds of dashboards. So you can make a device-centric one, which would pretty much be like the device list, like the app. If you click on each device, it's going to give you all the data from the sensors. And for example, all of our nodes are different as well. So some of them have a temperature sensor, some of them don't, based on the location they're at. So this is going to give you which one has which sensors as well. So what do we do with that data that we get? We pretty much trigger alerts. So for example, if one of the nodes detects high humidity, it sends a tweet. I'll show you an example of how it would look like, as well as an email to the admin saying, oh, this emergency occurred at this node, and it's going to have the data of the sensors, so the admin can see what happened. And this is a cloud-based emergency, but as we are speaking about security, emergencies are important because it's a matter of life and death. So this is cloud-based, so it comes later, but we also trigger emergencies at the node level. So locally, as soon as the emergency occurs, there's an alarm that goes off. Another cool thing is that we can do prediction. So for example, we can say if, let's say, a node detects water and there is a bit higher than usual level of humidity, then there is a possibility of a flood coming or happening. So then we send an email to the admin, just like before, and we send a direct message to the system admin so that people, the general public, wouldn't really know that there's a flood predicted, but the admin would know. So they would come or send a security personnel to go check the place out beforehand. And this is an example of how the tweet looks like. This is an actual tweet that was done from the campus safety department on 25th January, and this is how it looks. So in our case, it would be the same thing. So it's going to say emergency, this is a touch notification, but it would be an actual notification. It's going to go out automatically. Because it's an emergency, it's better, it goes instantly because there's no delay. Because if, let's say, we are waiting for a person to tweet about it, then people might not even know that there is an emergency. So with our system, it's automated, so it goes off as soon as it detects an emergency. So it's something on the campus safety department would have the same like location, time, and where it is happening. This is how the email looks for the admin. So it says humidity emergency and gives the date, what condition it was triggered at. So it's high humidity here in the device info. And this is the Twitter prediction message. So it says a flood is possible to occur near this node. Please take the necessary precautions. So then the admin would send a personnel to go check the place out. That's for the Bluemix. To put all the components together, we have our Zigbee nodes, which get data from all the other Zigbee nodes to multi-hopping, and they send the data to the Wi-Fi node. The Wi-Fi node is connected to the router, and it collects all the data from the surrounding neighbor nodes and then sends it from the router to the server. And then the server is syncing the data with the database. So the database has all of the logs from the previous sensors. And then the app is also synced with the server, so we can see real time the data that's coming in, as well as Bluemix. We can see real updates on the graph through Bluemix. And some of the challenges we faced while working on the project, first was Wi-Fi authentication issues. So we are using Raspberry Pis and they have Wi-Fi, but we couldn't really connect to the CU wireless or the ED room Wi-Fi connection. So we had to get our own router and then make our own Wi-Fi network to test things out. And the IoT lab helped us with that. The XB chips were also limited in size. So the chips we are using are not having a lot of data transfer rate. So we couldn't really, send videos or images through that. So we only have like text, which is the sensor data that's sending through to the Wi-Fi nodes. So we couldn't really do the media transfer from that. Constantly evolving IBM Bluemix. So when we started originally, IBM was changing the things they have in the Bluemix suite. So once we would log in and we could do something, the next day, the next week, we couldn't do it. So it was involving, so we had to wait and be patient with that. The last one is finding digital CO smoke sensors. It's very hard to find in the market. So Mohammed, he got the analog sensor, and then we had to make an analog to digital converter, which is what we're using now. So it's an analog sensor with the A to D converter. And with that, that's the conclusion of our presentation. We'll switch on to the video so we can see how the whole system works together. Research project. We are here in the tunnels today, 28th January 2018, and we have our nodes set up. We'll start with the app demo. We'll see Majeed giving all the nodes down set up already, with all updated information, logs, the interactive map, the updated information for all the sensors. Sweet. That's our first Wi-Fi node. It has a Raspberry Pi camera, a Zigbee that communicates with other nodes, which we will go into in a bit, temperature sensor, and that's a microphone, right? Yeah. And we also have Bluemix set up, and you can see from the graph that we are getting data from all the other nodes, and they're fluctuating right now. Let's go and see how it looks. How's it going here? Really good. So here's our first Zigbee node that's communicating with the Wi-Fi node, and you can see that's the Zigbee chip, Raspberry Pi and alarm buzzer, smoke sensor, and there's the air quality sensor. And that would be, sorry, go ahead. Can you introduce it? Let's go to the long side of the tunnel. So now we are here, and now we'll be walking all the way like this. That's another one of the Zigbee nodes. It's communicating with the other Zigbees through multi-hopping. Next one. Another Zigbee node. So if you look back, we can't even see where we started, where the Wi-Fi one was. So now that's our last node for the demo. So this is the last Zigbee node at the end of the tunnel. We are in the athletics area. So this node is now communicating with the other Zigbee nodes, and data is passing on through the Zigbee connection, and it's finally passed on to the Wi-Fi node, and that's pushed to the server from there, and Bluemix gets the data from there and updates it on the Bluemix stuff. We're right here, and our Wi-Fi node's over here. And now we've demonstrated an alarm for Zigbee, so we're gonna trigger an alarm here, but the Wi-Fi node here is gonna get the signal. So what are we gonna do now? So as we can see, the alarm just rang. And yeah, you see here. And right here in the app, we get the notification that I see a few. That line, you see the node that's getting the alarm. Awesome. Perfect. The video just got up to the drive and it's processing right now.
So this was for a separate emergency. This was for a humidity emergency, not for the original CO2.
That's the end of the presentation.